This week, we're looking at today a series of what I've called extension topics. They're kind of covering off extra bits and pieces from across the course that at the time of doing these sections I couldn't fit them in, and they're not in the exam. Having said that, the reason why I've got the word revision here is I'm going to highlight the stuff as we go that you should be able to understand, and there will be exam questions on. So this is both extra stuff but revision at the same time. Okay? And we're going to start by looking at multiple inheritance. So last week we looked at object-oriented programming and we looked at inheritance. Now, if you're coming from Java, in Java you can't have multiple inheritance. You can kind of get around this a little bit in Java by having a class that inherits something, but then also implements some interfaces. So your interfaces you can think of as being abstract base classes, and you can kind of achieve a little bit of multiple inheritance in Java that way, but it's not strictly multiple inheritance. In C++, you can have full multiple inheritance. It's not widely used, it is complicated, and if you're going down a path of using multiple inheritance, you should probably reconsider your design. However, let's show you what it looks like. So let's have a class of vehicle. Let's call it an amphibian vehicle. So an amphibian vehicle is a vehicle that can both go on water and go on land. Now, an amphibian vehicle might just be a class, if we're trying to represent this, that is both a boat and a car. So something that's both a boat and a car we could call an amphibian vehicle. So if we have this code and this class amphibian that inherits both boat and car, it supports both the public methods and also contains the data members of both boat and car. It has access to the protected data and methods inside those things as well. And the amphibian object can be upcast through references or pointers to either a boat or a car. Okay? And constructors occur in the order of listing. So this class, when it gets compiled, and the constructor gets called, when you call the amphibian constructor, the first thing it will do is call the boat's constructor, then the car's constructor, then the amphibian's constructor in that particular order. And of course, destruction is in reverse. I'm going fast because, again, this isn't in the exam, but this is, in a way, revision about how the ordering of these constructors works. So here's an example of multiple inheritance in action. We have a boat, and a boat has an anchor that you can drop or not, and it's just a boolean. We have a car, and the car you can open the sunroof on. Okay? So we can create a boat object and we can drop the boat's anchor. We have a car that we can open and close the sunroof on. We have our amphibian class, which inherits both of these things, and therefore we have an amphibian object that we can both drop the anchor on and open the sunroof, which might be helpful for an amphibian vehicle. You drive it into the sea, you put your anchor down somewhere, you pull out your fishing lines, open the sunroof, and you fish through the sunroof. Okay, so this works. Okay. However, this is an example of why we generally don't like the idea of multiple inheritance, because it very quickly leads to problems. Okay, so here is the same class again, only I've introduced two functions, both called drive. And so a boat, you can drive a boat, you can also drive a car. Okay? Now when I inherit off both of these classes, what do people think is going to happen? Nope. You have access to both somehow through a virtual table. Yeah, that's actually a pretty valid answer. Somehow is fair. Yeah. So the following code won't compile. What we had two slides earlier was we could happily call a.drop_anchor and a.open sunroof. That was fine. This won't compile now, this a.drive. And the reason is, and the error message is quite clean, the request for the member function drive is ambiguous. Okay? Because it has two drive functions. It's inherited the drive from car, and it's inherited the drive from boat. Okay, so you're exactly right in the sense of, yes, we've inherited both. They're kind of sitting on the V table somehow. but for request is ambiguous, so the compiler can't work out how to do it. So we can resolve this problem either using user code or class code, and it'll depend on exactly what you're trying to do, and also if you've designed these particular libraries yourself, or if you're using somebody else's library, how you resolve these. So there's 4 ways in which you can do it. And I've split them into for 2 user code ways of doing it and for 2 class code ways of doing it. So in user code, so this would say be inside our main function, we can have amphibian object, and we can call dynamic cast. Okay, so we've seen static casts all the way through this semester, but this is probably the first time you're actually going to see a dynamic cast in use. We can dynamically cast amphibian object A to a car reference and then call .drive. Okay? And that works. We can use what's called the disambiguation syntax, which is what we can call a.car : drive. And so this is like saying a.drive, but this car : bit is saying call the drive function that belongs to .drive. Sorry, call the drive function that belongs to .car. This, of course, looks very, very similar to your nested classes or your functions wrapped inside class templates and things like that. So that works. So that's the 2 ways of doing it in user code. You can, with your inheritance, because both the drive functions were virtual, you can overwrite the drive functions. And so you can create the drive function inside Amphibian, and inside that explicitly call the car drives function. Okay, so this means that this amphibian boat car thingy-bob, this amphibian vehicle, whenever you want to drive it, you're always going to end up driving the car bit. Now, that's actually not going to be very helpful for this example, because when you're in water, you can't drive an amphibian like you drive a car, but you could do that if you wanted to. And for final version, and this actually should be in red, so by the way, all through these lecture slides, I'm going to have quite a lot of red, more probably in the second half of the lecture, and the red stuff is the stuff that you should revise for the exam. So using car : drive, okay, so this is an exam type question. What does using car : drive inside class amphibian do? So this last bit here, what does this using car : drive do? And what does it make, how does it make things work?
It imports the drive from car into the namespace of amphibian.
Yeah, basically it plays around for scoping. So it brings that car : drive function out of the car scope, it brings it up into the amphibian scope, so it's treated as if it's the same scoping level, and therefore it works. So this version up here, this 3rd version here, we defined a whole new function. This 4th version, we didn't define a new function. We just changed the scoping on car : drive to come forward. Yep.
If we do the 4th option, then can we still use the 2nd option, disambiguation syntax?
Yes, you can. Yeah. So if you do the 4th version, you can then still use the 2nd version if you did want to switch across to it saying drive a boat in your user code. Okay. Okay, so that's multiple inheritance, a very fast overview of multiple inheritance. Again, you don't need it, or you shouldn't use it, but C++ has multiple inheritance. It wouldn't be a C++ course without talking about it. Okay, so let's come back and talk about templates. Okay? So we are going to be jumping all around today, but let's talk about templates. Now, imagine that this isn't a template problem, it's just a general coding problem. Imagine that we're trying to make a multiple dimensional grid. Okay? It could be 2x2 grid, or I could have a 3D grid, so basically a 2x2 and then it goes down that way. And the whole idea of having a multiple dimensional grid is X, Y, and Z, and however many other dimensions that you want. The length of those dimensions is all the same. So I might talk about a 2x2 or 3x3 or 4x4. These grids are always the same dimensions in terms of size. Now, I can make a one-dimensional length 10 grid using a vector constructor and give it a length of 10. That's fine. Okay. But if I want a 10 by 10 grid, okay, I would need to make standard vector, and call this, say, grid 2D and give it size 10. Now, this is only going to make me 10 vectors of standard int, and that's going to be that inner vector is going to be size 0. So that's actually not going to be a 10 by 10 grid. It's going to be a 10 by 0 grid. Okay? So we need to then figure out how to make the inner vectors also resized to be size 10 before we use this. Okay? Now, you could just do this all in vectors, okay, but this isn't particularly the best because we're leaving it up to you to figure out how to do this resizing. So we could write a class basically to wrap a vector, and if we wrap this vector, we can get the behavior right, okay? Everyone following so far? So here's a class that wraps a vector that does this multiple dimensional grid. Well, in this case, it's actually a one-dimensional grid, okay? So we have a template, okay? So we have a template. Again, that template probably should be in red because you will get template questions in the exam. We've called this 1D grid, and it's got a default argument of size of 10. Default arguments are in the exam. It's got a destructor. Destructor's in the exam. It has operator overloads for that square syntax to get value at a particular point. Okay, it's got two of those. One of those is just passing a normal reference. One is passing a const reference. Operator overloading and const references are in the exam. It's got a member function called resize, and it's got another member function called getSize, which just returns .size, and it's got this private T of m elements. Okay, so previous slide up here, we had this vector of ints. Okay, this time we want just a vector of T elements. Okay, so we could substitute into this 1D grid, and it would work fine. Okay, now this 1D grid is only going to be a one-dimensional grid. Okay. Now again, we want a multiple dimensional grid. Let's remember this thing's a template. Okay. So some implementation code, which I'm going to skip over. Okay, but you've got some implementation code. Let's go down and look at the user code. So the user code, we can create a single-dimensional grid. Okay, and pass it in int, and we back to having this one-dimensional grid size 10. That's cool. We can create a two-dimensional grid by having a 1D grid. Remember that 1D grid thing was a template, so we can have a 1D grid wrapping a 1D grid of ints, and that's now going to be a two-dimensional grid. Because if we scroll up, remember this is a vector of size t. Okay. And so what we've done is we've created a 1D grid that stores a 1D grid. Okay, if we scroll back down, we have literally created a 1D grid that stores a 1D grid of ints. Okay, that's fine. And that will have size 10 by 10. Okay, because for default arguments, okay, size 10 there inside the constructor. Inside the constructor itself, okay, where's it defined? Here it is. It calls, see our private data member called melements, it calls melements.resize. Okay? So when we create 1D grid int, what happens in terms of our constructors is this 1D grid goes and creates a singular, first object it creates is a 1D grid of ints. Okay, so it creates one object there, that 2D grid object. Because of the call to resize here, it then creates 10 just 1D grid int objects. Okay? So overall in memory, we end up with 11 objects in memory. We end up with 11 vectors in memory. Okay? Because the first vector wraps size 10 1D grid ints vectors, and then each of those in turn wrap a singular vector each, but it's 10 of them, and they wrap a vector of ints. Okay? Now we can do this a third time to do 1D grid, 1D grid, 1D grid int, and we get a three-dimensional 10 by 10 by 10 vector, okay? And also because the way in which we've got our operators defined like this over here, and we're turning references to t, we can use these things to put values into certain places, okay? And so we've solved this resizing problems. The n-dimensional grids can be generated through these recursive types, okay? But the nested types are really messy, okay? So 1D, 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 blah, is really messy. So it would be nice if we could write just nd grid, int, and then give it a number of dimensions. So, for example, we could write a three-dimensional grid just like that. That'd be a nicer way of doing it than this messy syntax, right? So how do we do this? We're going to do this for a thing called a recursive template, okay? So this previous code here wasn't recursive in the sense that the template wasn't recursing on itself. The user code kind of treated it a bit like it was recursing, okay? But it wasn't strictly. So this is kind of, up here was kind of like a recursive type, whereabouts we're going to now do a recursive template, okay? So the recursive template looks like this. Taking the type name as before, we then take in a size t. Now, size t is just an unsigned int, okay? So we're taking in an int value, okay? Now, because this is recursive, we can do our standard recursive function of calling like n minus 1 to keep on recursing, keep on changing the value of n. And so, particularly down here, this private field, a standard vector, whereabouts before, if we go up a couple of slides, the standard vector here was of type t. This standard vector now is of type nd grid, which is the class up here, okay? But it's of t n minus 1, okay? So this compiles because this type here, this nd grid here and this nd grid here are different types. Because remember, with a templated class, you get a different type generated for each thing that it's wrapping. Okay? So this template is recursive. It's recursing on itself, okay, but with n minus 1, so it's generating a different type each time, okay? And like I said, point out that for operator, square brackets are returning now these nd grid objects, not t objects. So again, we got 2 slides. This is returning this base t data type. This is also returning recursive data types as well. So we have this recursive template. How are we going to program this recursive template to stop recursing?
Another type with a 1 in the template.
Another type with a 1 in the template. Okay. What's the name of that?
Another class with the same name but a 1 in the template.
Yep.
Declaration.
Yep. What's the name of this? What's it called? What do we need? Because you've basically summed up what we need to do, but what's the name? Again, this is exam sort of revision. What's the for technical name for the type of class that we're going to create?
Specialization.
What specialization? Okay, we're going to take it. We're going to create a partial specialization. Okay. And so we have a second templated class. Okay, we have a second templated class with a 1 up here. Okay, so this is for base type. Keeps the t there. Notice that for return types here are now returning t's, whereabouts before they were returning the recursive type. This private vector is now storing for t elements. Okay, and when we get as far as the user code, those implementations, when we get as far as the user code, we can say, this is the nd grid of ints, we want 3 dimensions, there's my 3D grid, bang, works just like that. Okay, now that code there is a lot cleaner than that code there. Because this code here, if you stuff up however many dimensions that you want, and you get it wrong, you can easily make mistakes. This one here, you're being very specific just at that point about what dimensionalities you want. Okay? So, in the same way that we can write functions that are recursive, we can write templates that are recursive. Okay? And the whole reason why you do this is going back to that first example of how do you go and make a three-dimensional grid. This recursive template is hopefully a lot cleaner and a lot more bug-free than you trying to just manually resize vectors and do stuff like that. So if you plug this all nicely into a vector, sorry, not in a vector, you nicely wrap this vector up into some classes, it will hopefully cause you less problems and less bugs in your code. Okay? So staying on the topic of templates, okay? Staying on the topic of templates, we're now going to talk about type traits. Okay? So, who remembers type traits? Yep. So we did templates. We did templates. We did function templates, and then we did class templates, and then we did custom iterators, and everyone hated me. And then we did type traits. And so for the function templates, for class templates, for custom iterators, and then for type traits are all related. Okay? Now, what is a type trait? What is a type trait and how do we use type traits?
Values which are defined based on certain properties of the type that you can use.
Not really. You half there. The value tells us something about the type. Yeah, we get some sort of value, but that's not the type trait itself. What is the type traits library? Or what is a type trait? How could we write a type trait? Oh dear. Let's go back to the lecture slides from that week, okay? So if we go back to type traits, okay, it was Monday of week 8, okay? Translation should be in here. Okay, Monday of week 8, let's go take a look at this. Okay. So we had these numeric limits. And that was actually in week 2 we had those numeric limits. And numeric limits allows us to say get the maximum value of an int. Now, the type trait library for limits looks something like this. What is the name of this? So what is the name of this sort of type of coding? Partial specialization again. Okay? So the type traits are simply classes themselves. Okay? Template classes themselves that are specialized on particular types to tell us particular information. Okay? And so we looked at numeric limits, and then we looked at this function for isVoid. Now, how does this work? How does this class work? Like, as in, first of all, what's the output? Like, the output should be obvious. What's the output going to be? False true, yeah. But can you step me through how this works? As in, step me through line by line. So this is void int. What am I going to do? I'm going to go up and I'm going to match this template up here, right? Is void void. I'm going to come up and I'm going to match this template up here, right? Why is it going to match this one? Surely it matches this one. Why doesn't it match this one?
Correct specialization for full specialization?
Yeah, so for full specialization sitting in here, has priority over this. Okay, this has priority over this. Okay? The same can apply for isPointer. Okay, so notice the difference here. This is a full specialization here, and this is a partial specialization. Okay, because that's got type T and that's got the full type. Okay. And so this is type trait library, and we looked at the idea of is void, is integral, is floating point, is class, is pointer, is L value reference, is R value reference. There's a whole lot of them. In fact, and again, you don't have assignment 3 marks back yet, but I actually use type traits to check your iterator. So I used the type traits library to check if your iterator was doing the right thing. The reason for doing that is I couldn't be bothered looking for your code to read it myself. Instead, I just wrote a thing that said, is the thing that that your iterator is returning, is it const and is it a reference? I use the type traits to work that out. Okay? And so we can write code. Actually, this is probably a good example because we're going to come back and take a look at an example that's kind of like this in a few minutes. But we had this a test of number function. And this test of number function used the type traits to see if something was an integral or something was floating point and told us if something was a number or something wasn't a number. Okay? Now, we also looked at type transformations and all that sort of stuff. We're not going to go back into that for now, but again, this stuff is in the exam. Okay? So that week 8 lecture, actually all of this week 8 lecture, there's questions in the exam on this week 8 lecture. There's a number of them. Okay? So if you're weak on your type traits, this is what you should be looking at. Okay, let's go back to looking at type relations. Oops. Let's go back and do that. Okay. So we've recapped on week 8, okay? So, let's go back and take a look at this function. We're using the type trait is same. Okay, we're using the type trait is same. Now, what do people think is same does? Yeah, checks if it's the same type, and obviously it returns a Boolean. And so we can use the value of this Boolean to write a function that says, the value of T1 and T2 are of the same type, or they are of different types, okay? And so if we run through 1 and 32, well, 1 is an int and 32 is an int, so they're the same type. 1 and 3.01. 1 and 3.01, are they the same type? They're not the same type because 1 is an int and 3.01 is a double. Okay? Now, if I had a function called same, so additional function called same, and it took an int and say took another int, what would it get called? Would for 3.01 get converted into an int if I had just a normal function called same, or would it get compiled out to the template? So if you cast it to an int, then yeah, it would call the right version. Otherwise, it would go, it's not for, there's a template that we need to construct, okay? So 1 and 3.01 are not the same type. 3.01 and a string, well, I sure hope that those are not the same type. So you can use these type traits to write a function that tells me if things are the same type, okay? Is everyone still with me at this point? Because this is the easy stuff. Okay? Yep. So what we're going to do is we're going to take this a step further. We're going to take this a step further. So what we just saw on the week 8 slides was there was a templated class, and then there was these specializations, and these specializations got favored over the idea of the templated class, okay? If I have a templated class, though, if I have a templated class, what does that mean for my code? So say I had many calls to the same, and I kept on just throwing in lots and lots of different things. What happens every time that I call same with different types going in? I create a new template function for every single different version of same that I attempt to call. Okay? Now, that's what makes templates very powerful. You know, we write a generic container because we want a container to be able to store many different types. Okay? But what happens if we wanted a function, a templated function, or maybe not a templated function. What happens if we want a function that works for, I don't know, we want a function that only works for numbers. Now remember with numbers, we've got shorts and longs and ints and floats and doubles and complex numbers. We've got a lot of different number types in C++. What happens if I want to write a function that only works for numbers, but I didn't want to do casting, I still wanted it to be a templated function? Could I do it? Yeah, but I'm going to do stuff with type traits, but yeah, what else am I going to do with it?
Your slides are great, but it's something I did in assignment 2, which is enable if.
So some people did enable if in assignment 2. Enable if is complex, and yes, that's what we're about to get into. Okay, so we're going to look at the idea of having a templated function, but it only gets enabled if certain type traits are true. Okay. So this idea of enable if can be used to disable certain function overloads based on type traits. Okay. This enable if function or meta template, okay, takes two type parameters. The first is a Boolean, or something that's going to compile out at compile time. So this is through metaprogramming, okay, to a bool indicating if this template function should be enabled or disabled. Okay. So we use the type traits to determine value for bool. So this is metaprogramming. Okay. There's no metaprogramming questions on the exam. Okay. No metaprogramming in the exam. There is type traits questions in the exam though. Okay. The second type that we pass into this thing called enable if, okay, is the type parameter passed through to the nested type. Okay. So if we want to enable something that worked for, say, ints, if this thing was true, the int would get passed through. Okay. If the Boolean is false, the second type parameter is not passed through, and we can end up with compilation errors. Because what we can have is we can end up having a function, and we'll see it in a few minutes, we can end up having a function where there's no return type. And with the exception of constructors, you can't have a function that doesn't have a return type. Okay, so you'd normally get a compilation error. But enable if is special. It's an example of something we call substitution failure is not an error. Okay? And so substitution failure is not an error, is to do with the compiler, and it basically will disable a function overload if something is about to result in an error, but instead of actually giving an error, if there is a different function overload that will compile, then no error is generated and the code keeps on running as happy as it is. Now that's a lot of text and a lot of explanation. Let's go for an example. Okay? Here is the same function as before, split into two different versions. Okay? So before we had a function called same, and that used the type traits to work out what to print. This function, or these two functions, are going to, one of them is going to work if the types are the same and be generated for that situation. One of them is going to be generated if they're not the same. Okay? And we're going to do this via enable if. Okay? So if we look at this very carefully, we have this templated type, T1, T2. We have this function called check type. The return type of this check type function is this ridiculously long line here. And so what we're saying is this return type is going to be a Boolean. Okay, so let's go all the way back to here. Let's read it from here. This return type of this function is a Boolean, but only enable this return type if, according to the type traits, T1 and T2 are the same type. And get the value of that. So if that's true, now enable if only works if it's true, then get the type of this. If this is false, then this type doesn't exist, and therefore a compilation error is generated. Okay, so this enable if sitting up here is going to say if the return type of this is a Boolean, if they're the same, but because of enable if they're not the same, then no return type's generated, not void, it's no return type's generated. You can't have a function without a return type, so an error is generated. Okay? But if we go down to the next template down here, The next template is exactly the same as one above, with the exception of this exclamation mark sitting here. And so this exclamation mark sitting here says is same. What's the value of this? Not that. Okay? So basically, if things are not the same, then it's true. And so it comes through grabs for building and value. And so if the values are the same, this function gets generated. If they're not the same, this one gets generated. And because we've covered off both situations, both the true and the false situations, despite this one generating a compilation error, if these things are the same type, because of this idea of substitution failure is not an error, this version will get compiled instead. Okay? If you leave out either version of these, if you leave out either version of these functions, then you will get a compilation error for one that doesn't work, because this idea of substitution failure is not an error. Says basically, if there is something else I can substitute into, then I'll keep working. If there's not, then I will generate an error. Okay? So where am I up to? Okay, so I've got another example of this coming. Okay? But this is quite an advanced idea. So this is bringing together all the ideas in terms of type traits and templates and substitutions and things like that. Okay, so we're attempting to enable certain functions in our code if and only if certain types are true. I have another example of the idea of substitution failure is not an error, and it doesn't involve type traits. Okay? Here's the second version of it. Okay? This second version, okay, and there's quite a bit of comments and codes on the screen, okay? But I have three different functions here, okay? I have a normal function called test, and test just takes in ... okay? So ... is a wildcard match anything, okay? I then have a function that the return type for this function test is getting this class C, attempting to dereference it, and getting the type of the dereference of C. Okay. This one up here is trying the same thing as a function. Okay. Now, if you attempt to pass in something that you can't dereference, or something that you can't treat as a pointer because it's not a pointer or it's not a reference, then you're going to get a compilation error. Okay? But because of the idea of substitution failure is not an error, so test up here, test in here, and test in here are three different overloaded functions. Remember, function overloads work on parameter types and also work on for name matching. So we've got three functions, they've all got the same name. The template is only going to be generated if it can actually properly generate it. So if there is an error, it can't generate it. Okay? We're going to exploit this idea of these trading return types and also the variadic function up here. Okay? To basically write these three functions that basically say if the pointer version of this, if the reference version of this, or if the catch-all has been called. Okay, and this, by the way, this example is taken directly from cppreference.com, and their example of this idea of substitution failure is not an error. So here's some user code. In this user code, we create a class or a struct just called x. It's got this function called void f inside it. Inside main, we create a type of x, okay? And then we call this test function 3 times, okay? The first time, it gets passed in by reference. Gets passed in by reference. The second time it gets passed in as a pointer because it's the address of x. Okay? And for third time, it gets passed in some R values. Okay? And so the first function, of course, the reference overload was called. The second one, the pointer overload was called. And the third one, the catch-all was called. And so this code up here combined with this code here compiles and runs happily. Okay? So the summary there with enable if and also with this idea of substitution failure is not an error, is we can enable or disable parts of our code based on type traits. Okay? So going back to the example I had earlier, we could use the substitution failure as not an error to maybe use the type traits for is integral or is floating to write a function that will work for all types that are number types, okay, but doesn't get generated for anything else. Okay? So templates are good because they allow us to make our code very generic, but then sometimes our code becomes too generic, so we take this back in and restrict things based on the properties of our types. Okay? So I've got one more example here. It's something called static assert. Okay? Now, when we talked about exceptions, you probably heard me say about how much I hate asserts. The reason why I don't like asserts compared to exceptions is asserts get thrown and just terminate your code, okay? And asserts are really bad if you're writing library level code and you're terminating somebody else's program. You shouldn't be doing that. You should be throwing exceptions. The other thing to do with asserts, and this is what I did in assignment 3, is I can just disable for asserts at a compile level flag. I can't do that with exceptions. Exceptions get compiled in at runtime. I can't disable them the same way I can disable asserts. Now, a static assert is an assert that happens at compile time. Okay? And again, we can combine this idea of static asserts with type traits to, again, not so much enable or disable a function, okay, but to just not allow a function to be compiled at all if some sort of type trait isn't true. Okay? So I have an example here where I have I've got 4 classes. Okay, I've got a class base 1 and then a child class of base 1 which inherits from that. I have base 2, which is a child class of base 2, which inherits from that base as well. So I've got 4 classes, okay? And 2 of these classes inherit. I have a templated function that will take in a type T. So it should be generated for all 4 of these things, okay? But I have inside the top of this thing called a static assert. And the static assert looks at the type traits of this T in here and says, is this T a base of this base 1 class? Okay? And because of the static assert sitting in there, I can happily compile base 1, okay, because there's base 1 a base of base 1? Yeah, it is. It's kind of saying, do you inherit from yourself? You can. Is base 1 child a base of base 1? Yeah, it is, because base 1 inherits from base 1. However, if I attempt to compile with base 2 isn't a base of base 1, so there's a compilation error there because of the static assert. Okay? So static asserts allow us to basically put into the compilation stage of our code checks to make sure people are doing the right thing with our code. So what I said before, again, if you're trying to write a function that only works on numbers, there's 2 ways in which I can do it. I can do it with enable if. I could do it with enable if and some sort of big long error message would come out. Alternatively, I could do it with a static assert. And the static assert, I could say this thing's not an integral or not a floating point number, and therefore don't compile. And the error messages are going to be different. So let me just see how much code I've got here. Yep, so what I'm going to show you is I'm going to show you this enable if version. Okay, here it is. And I'm going to attempt to compile this. Okay, so G++ standard equals C++ 11. Enable if, okay. and that goes away and compiles, and it runs perfectly fine. I take out one of these functions, okay, and because of enable if up here, when the values aren't the same, that's not going to compile, okay, and so I compile this, and I get this no matching function call error. There's no matching function call error because I can't find a version that's int and double because it didn't get compiled. Yep.
Instead of calling out the whole function, if you just change the type to return bool.
Okay, so you want me to change this to return bool?
Yeah.
Okay, that's going to be easy. What do you think is going to happen? I don't think it's going to compile. Okay, I might be surprised, but I'm pretty sure this isn't going to compile. Okay, I'm pretty sure it's not going to compile, and the error message is going to be redefinition of the same function. Okay, let's see. Oh, no, it actually compiled, but we have an ambiguous function call. Okay, because now there is two types that both take in a T1 star and a T2 star, where this is an int and this is a bool, and this one's a bool, and this is whatever this is, but compiles out to be an int. Okay, is that a question or a stretch? Stretch, cool. Okay? So, no, you can't just put bool into there, okay? So, this enable if needs to cover both of these circumstances. The static assert, on the other hand, okay, which is sitting down here, here's my static assert function, okay? If I attempt to compile this, with the static assert thing in there, let me clear that screen, but the error message is different. This one says the static assertion failed. With our message, a base 1 should be a base for t, okay? So see how we put the nice little error message into our static assert up there, okay? So basically that got errored at compile time, and this static assertion error, in a way, is much nicer because we've written that error message. So unless we write stupid error messages, okay, that should help us a lot with debugging. By the way, speaking of stupid error messages, do not throw exceptions or write error messages that look like that. It tells you nothing. So again, like I said, you haven't got assignment 3 back yet, but anyone who threw an exception that didn't have a message inside it, we took marks off because that's not a helpful message. That tells me nothing. If you're throwing an exception, you should give some sort of why you are throwing this exception, okay? Okay, so at this point, I'm going to stop for a few minutes. Now, I'm going to leave you with a problem to solve during a break, though. So after a break, we're going to talk about 3 things. We're going to talk about circuit dependencies. We're going to look at the source code of unique pointer.h, okay, in the STL library, because we should be at a point now we can actually read STL source code. And we're also going to then talk very briefly about performance and how we can get performance out of C++, minimizing speed and also processing power. While we take a 5-minute break, if you've got your laptops, attempt to code up this makeimage.h and this display.h and attempt to compile them and see if you can figure out how to make these compile, because they don't. Okay? We'll pick up in 5 minutes. Okay, so let's resume. Did anyone code this up during a break? You're doing it now? You're doing it now? How far off fixing it do you think you are?
We're just compiling.
Okay. And does it compile? Yes, no. What do you mean? You got one of them to compile? We're going to guess no. Okay. So we have these 2 functions. Or it's not 2 functions, sorry, it's 2 header files, okay? And basically this comes from, and consider we have a really, really big software project, okay? With lots of .o files and lots of .h files, okay? This example is actually motivated by a problem that some of the people had in RoboCup a few weeks ago, okay? So Sean next week might talk briefly about some of the RoboCup code base, but the RoboCup code base, you have a lot of code, and you don't have one program that's got main, you might have a couple of different functions. And so they basically had a program that went and produced some images, okay? Literally it worked on a robot, it got some images from a camera of a robot, okay, and pushed them up to a data structure, okay. There was another program that displayed for images, pulled for images in off this data structure and displayed for images, okay? And so this is kind of a bit like a producer and consumer type problem, okay? We have a producer class, okay, called makeImage, and makeImage has a function that, or a member item that says display to send for images to, okay, and that's stored as a reference. The makeImage class also has this image class, okay, and this image class can just be like a two-dimensional array of 800 by 600 for argument's sake, okay? Now, this makeImage class needs to hash include display.h because it needs to know about display, okay? The display.h file itself has the definition of the class display, has this function called receiveImage, okay, so inside makeImage it might say display to send image dot receive image. It might call it that function through, and it passes through a reference to an image. And it also has an image, and it's not a reference, it's got an image of last image received. Now the reason why it's not a reference is because it might have to store the last image it's received. If this was a reference, it could end up being overwritten while it was doing something, and makeImage up here could end up overwriting for reference to it, okay? So this needs a full copy of the last image received. It can't be modified, okay? So that's why it's a copy of it. Now, how does hash include work? When I write hash include, what does the compiler interpret that as doing? Inserts all the code at that spot, okay. So I do have a display .cpp, and so my display.cpp, I think it might be on the next slide. No, okay. I've got this display.cpp, I'll bring it up on this laptop. Okay, here's my display.cpp. It literally hash includes display.h, and this has the definition of the receive image function. Okay, so this in compiling display.cpp will hash include display.h. So I take a look at display.h, and display.h hash includes makeImage.h. So I look at makeImage.h, okay, and makeImage.h then hash includes display.h. Okay, so display.h is hash including makeImage.h, makeImage.h is hash including display.h. Okay, so we've got basically a circular dependency going on at this point. Okay, now what I've got at the top of this, okay, is, and I'm using a slightly different type of header guard, but it's the same thing. I've got header guards on these .h files. Okay, so these header guards on these .h files will break that piece of the circular dependency. Okay. So when you get to makeImage.h and it says hash include display.h, it will go, hold on a second, I've already hash include display.h. So I'll go down and I will create the class image. I will then attempt to create the class makeImage. Now makeImage relies on display. Remember that display isn't declared until down here, but we've hash included makeImage.h, okay? So we haven't got the definition of display. So this isn't going to compile, okay? If I attempt to compile this, so if I attempt to compile, so just C, display.cpp, it doesn't compile because display does not name a type, which means that it's got to this, can we use display? And it's going, I can't use display, it doesn't name a type. Okay? Which is exactly what you're seeing over here, okay? So display.h hash includes makeImage.h for image class, okay? But makeImage.h needs the class display declared to compile the rest of the header file. How do we fix this? This is interactive. How do we fix this? How am I going to go make this thing compile? No, I'm not going to move the hash include further down. That was one of the PhD students' suggestions, and it works, and it's terrible style, but we can try it. Okay, let's try it. Okay, we're going to move the... where do you want me to put it?
Just before we need it.
Where do we need it?
I guess inside like the class, yeah.
What, you want it?
Yeah.
You want it here?
Yeah.
We put it inside the class as well, just to make sure.
Display does not name a type.
We didn't include enough times, bro.
Display does not name a type.
The other side as well.
Okay, nope, still doesn't work. Okay. Let's just whack it at the bottom, eh? Nope. Okay, so no, that didn't work.
A separate header file. For both.
For both what? Wait, what? What are you going to put in a separate header file?
Just the definitions of the No.
Wait, you want me to create a header file
Header.
that just says... Is that what you're suggesting?
Yeah.
Okay, so let's do this. You're still wrong, by the way, but let's just do this. Okay, and I'll whack the header guards on. Okay, so Pragma once is just a type of header guard. Let's save this into depend. Deck.h. Okay, so you're telling me that I should hash include deck.h, and display.h, and in make image. Okay. And let's go compile this. Oh, display compiled. Okay. So display compiled, that's cool. Let's go and try to compile make image. Oh, now we've got an incomplete type. So we managed to get one thing to compile, okay? But now when we try to compile, because remember this is a circular dependency, now when we try to compile that away, now we've got an incomplete type, okay? So what you guys basically did in a slightly different way is you basically did this, okay? You forward declared display into makeimage.h. It's essentially what you did. You just actually forward declared all the classes, okay? And so display now compiles, but makeimage doesn't, okay? And so it's a slightly different error compared to what you guys did, but see, I had this issue about image does not name a type. Because we've forward declared image, okay, with that header, image is now a type, but it's an incomplete type. Does anyone know what an incomplete type is? Yeah, so an incomplete type means it's been declared, okay, it's been forward declared, but the rest of the information about how the class works hasn't been found out yet, okay, so it's incomplete. Now, an incomplete class, we can create references and we can create pointers to, okay? So maybe if the solution to all our problems is just inside makeimage.cpp, we just make this a star, okay? And then let's try and compile it. And, oh, actually, it still doesn't compile, okay? Still doesn't compile. Okay, so that didn't solve our problem. I was surprised. I thought it might have, okay? Still doesn't compile. Let's take a closer look at this. Oh, because let's read the error message properly. So we're inside makeimage.cpp. We then went into the header file. We then went into the .h file, okay? And so let's read this from the top down. Okay, let's take a look at makeimage.cpp. Okay, makeimage.cpp, most exciting CPP file in the world. It just hash includes makeimage.h. Makeimage.h hash includes stupid forward declaration class, but that's fine. We then hash include display.h. Let's go across to display.h. Display.h hash includes makeimage.h, okay, but doesn't because of header guards. We go into display, oh, image. Image isn't, make this a pointer, okay. Make this a pointer. I think it might compile. It does. Let's try and make display. Oh no. Now we've got can't cast, okay? So we go fix up display, which is down here somewhere. Do that. Nope, still can't do that. Somewhere in an assignment somewhere. It's in the CPP, is it? Okay, so in the CPP, oh, that needs to be a pointer. Okay, I'm not going to fix this because this is wrong. Okay, the reason why this is wrong, okay, is remember I said this last image received has to be an actual image. The reason why we don't want it to be a pointer is because if it's a pointer to something, someone else can go change it. If we're displaying an image, we don't want the image to be magically changed halfway through what we're doing, okay? So we are stuck, maybe. We're not actually completely stuck, but we're stuck. Display compiles, but make image doesn't compile, okay? And it seems that everything we try to go and do is doing two things. It's either fixing one problem, breaking a second problem. Alternatively, what's going on is we're going, oh man, we've got to go change that to a pointer and this and that and something else, and we're changing so much of our code, and we're not actually solving the problem. All we're doing is we're shuffling the problem around, okay? And literally, well, for technical term, I'm not joking about this, is this is dependency hell, okay? Technical term for this is dependency hell. Everything is going wrong, okay? So, how might we fix it? Put it all into 1.h file, sure. Like that? Like that, done? Okay, that one works. Ah, I was surprised that actually works. But that actually works, but again, we've changed what we're trying to do. Okay, go back to a first example. The first example that we talked about, was that, again, we have maybe a make image might be running on a robot, okay, and display might be running on a computer. Now what we've done is, because we've whacked all this stuff out into one file, in order to compile this, say, image viewer, we're now going to have to compile all this junky robot stuff that we don't need to display the image, okay? And so the whole idea of separating things out into smaller files is that we don't need to compile lots and lots of stuff, because if we compile lots and lots of stuff, our program literally becomes huge. Again, we introduce potentially extra bugs into our code because we've brought all this additional functionality we don't need in. So our code goes slow, we've got too much stuff, we've got potential to put in bugs. This is not a good solution. And in terms of coding style, this is not a good solution. Okay? So I'm surprised that worked, but that works, okay? But let's say that's not the right answer, okay? So that's not the right answer. Let's go back and put that back. The answer is actually the opposite. The answer is, instead of putting everything into one file, is actually separate some stuff out into separate files. And so we separate out our image.h, our display.h, and our makeimage.h. And we have display.h hash include image.h, we have makeimage hash include image.h, and then display.h, and then everything is happy. So if I close all this and actually just go to the solution, okay. So if I take a look at this now, we have this image.h. So we just moved image off into its own .h file, okay? And then display.h hash include that, makeimage.h hash include that. We go to compile this stuff, display compiles, and makeimage.cpp compiles, and we're happy, okay? And so what we've done is we've broken the circuit of dependency, okay? Because remember last time we had display hash including makeimage and makeimage hash including display, okay? We've broken that circuit of dependency, and what we've done is basically this class image basically becomes, for lack of a better term, a data type, and so we have some sort of like data types.h file. Again, if we have time next week, which we should do, Sean hopefully will go into a whole lot more details about how RoboCup actually deal with this, because once you go to a big project, whereabouts there isn't necessarily just one main function, these problems come up all the time, and resolving them is very, very difficult. You can spend hours working on them. Okay? I'm getting a smile from a person who, how long did it take you to solve it?
Longer than it should have.
2 days?
Something like that.
Yep. So the point being is understanding, first of all, what the error message is, and don't just arbitrarily just go move stuff about. You arbitrarily go and move stuff about, you actually, so say our moving of make image into display, okay? We might have solved our problem that time. Someone else comes along, tries to do something, and they hit the same problem, and your fix for it has actually just made things worse, okay? Okay, so now we get to do some exciting things, okay? So, in terms of covering off template recursion and enable if, and a little bit of circular dependencies today, throughout this course, we're now up to a point where we should be able to look at the STL definitions of actually how the guys that go write, the actual compilers go and write their code, and we should be able to understand it. Okay, so I've got a link here. Hopefully it opens up. Okay. And so this link is going to be to the source code for unique pointer.h. So when we go use a unique pointer, remember we've got 3 different types of smart pointers. We've got unique pointers, shared pointers, and weak pointers. Okay? We can now go take a look at unique pointer.h, and we should be able to understand it. Okay? So, easy. What's this? Header guards. Woo! Okay, we've got some header guards. We've got some hash includes. We have a namespace. Okay? In this case, it's a namespace standard because unique pointer is part of namespace standard, okay? But we have a namespace, okay? Now, it's going to be bits and pieces like this all the way through. These are extra debug symbols going into the compiler itself. We can ignore those. But we should be able to look down this and see interesting things, okay? And so, I mean, like, what's this? A template struct, okay? A template struct, which is basically a class. You can take a look at this, and this one takes a little bit of time to work out, but this should be pretty obvious what this is. If we have a class or a struct called default delete, what is this? It's a constructor. The const expression on the front of it just means that it can be used as a const expression at compile time for metaprogramming purposes. What does for no except flag mean? You can't throw an exception, okay? And for equals default means that here's the definition of a constructor. Generate me the default version of the compiler's default version of this constructor, okay? We have here a second template here. Whereabouts the second type name coming in, first of all, is equal to something. So what does this mean? Type name equals something. Forget about the rest of this line. What does type name equals something mean? What's that giving it?
Default parameter.
Giving a default parameter. Okay. So here's a template. Okay, it takes in whatever the UP type is and a default parameter. This default parameter is the result of an enable if. Okay, so we looked at enable if earlier, and so the enable if is saying, can we convert this the pointer UP star to this whatever this TP star is? Okay, so we've got this UP here, we've got this TP here. So are these types convertible between each other? Basically, are they pointers to the same type? If they are, we can create this templated type called default delete. It takes in a default delete const ampersand. Now, what is a constructor? It takes in a const constructor to itself by reference. Copy constructor. Okay. We can then go down. We can take a look at this here. If we've got a class, we've got a void operator just like that. What's this? There's a couple of things going on there. Sorry?
Is it a functor?
It's a functor. So that's an operator overload, and it turns this entire structure up here into a functor. Okay? We then scroll down. Okay, we can actually read the comments and see there's a specialization. There's a specialization on just the square brackets, which is a specialization for when this templated type is actually a C-style array over some types. Okay? And again, we can take a look at all these type traits and these type transformation libraries and keep going like that. Now, this code is long, okay? So I'm not going to step you line by line through about 1,000 lines of code, okay? Too much code, okay? But you should be able to sit down, if you really want to, work out how this unique pointer is working, okay? Which is actually what I did on Friday. And so, because I have no life, so for you, I'm going to give you the important stuff for unique pointer.h, okay, and highlight how it works. But again, this is about the red highlighting of what we're going to show you down the bottom, the stuff that you should revise for the exam, okay? So here we go. So we just looked at this default delete, okay? But this default delete has a constructor that's a const expression no except equals default, okay? We had for enable if, which we saw earlier today, and we had for functor, and also we had for static assert here, okay? And it's interesting to see a static assert is looking at the size of whatever this thing is and seeing if the size of it's greater than 0. So if the size of a type is 0, therefore it's not defined. Okay, so it's an incomplete type, which we just saw in that circuit of dependencies argument. So in one struct, in this 15 lines of code, we have a const expression, we have a no except flag, we've got enable if, we have type traits, we have functors, and we've got a static assert. Okay, in 15 lines of code. Okay, the lines in red down here, for keywords in red are the stuff that you should know for the exam. Okay. So what's a functor? A function with a function operator is overloaded. No.
A function object.
Sorry?
A function object.
Well, yeah, a functor is a function object, but what's a function object? If you're in your exam, if the question says what's a functor and you write a function object, that's not the right answer. Okay? What is a functor or a function object? So it can be used like a function. A functor or a function object is a class with the call operator overloaded, so the object can be used like a function. Cool, that's 1 mark. Let's go for 2 marks. Where do we use functors? No, we're not necessarily. Where do we use functors? Why do we write a functor?
So that we can pass a function as parentheses to some other function. It's kind of a functional programming way, but it's not exactly the same.
Yeah, but can you give me an example where you'd use it? Standard sort. Okay, so if the question said, explain how you'd use a functor, again, that first level answer was good, but giving that example, concrete example of how you'd use it. Okay, that's what you should be looking for. Okay, so if the question said, explain for use and purposes of a functor, okay, do not write a functor as a function object. Okay, that won't give you any marks. Okay, because I know a functor is a function object. If you go and say a functor is a class that behaves like a function because it's got the call operator overloaded, okay, that might give you 1 out of 2 marks. We use this, for example, in standard sort, whereabouts we give it its own comparison operator. Okay? If you're going for extra marks, you can say a lambda function gets compiled to a functor. A lambda function gets compiled to a functor. Okay? Okay, so we looked briefly in that code bit up there of this template specialization. Okay? So we've got the same template here is specialized on this particular type. Again, this is also a functor. And we've got enable if, okay? So no questions in the exam on enable if, but we do have questions on template specialization, particularly related to type traits and things like that, okay? And we looked at template specialization in the first hour of today, okay? So what we've got so far in unique pointer.h is we've got a struct called a default deleter. We have, or a functor called a default deleter. We have then a specialization of this thing called default deleter. Okay. When we talked about smart pointers, I took these slides out, not these ones exactly, but I took some slides out about how you do a deleter, because it's kind of a bit dumb. But when you have smart pointers, instead of just having the smart pointers have the default behavior, you can write your own deleter function for them. The purpose of having your own deleter function is you basically end up wrapping the smart pointer or giving the smart pointer some overloads on how it deletes memory, how it does reference counting and things like that. So if we go up and take a look here at this delete here, this specialization just calls delete square brackets on pointer. Okay? So this default deleter manages how the new and delete calls are handled. Okay? You don't need to care about that level of detail, okay? But again, you should know that smart pointers do reference counting, and smart pointers also wrap objects, and when the smart pointers go out of scope, when the reference count goes to 0, if you're talking about a shared pointer, then it gets deleted. To delete it, the deleter gets called. Okay? And so here we go. In our unique pointer class, we get down the code a little bit more, and we have a template function again, okay, with a default argument, so it gets the default deleter, and we have a class. Inside this class, we have another class. I wonder what that's called. Okay, so we've got some inner classes going on. Okay, this unique pointer actually has an inner class called a pointer that basically has some random thing sitting here. And this random thing sitting here, again, you can work it out. Okay, the random thing sitting here is you've got these, oh, it's gone off the screen, but basically you have these pointer types here, and you're trying to convert this TP object down into this pointer type, and then you create a pointer of whatever the unique pointer is wrapping. Okay, so again, complex code, but basically all it's doing is using type traits to sit down and work out the thing that you're trying to turn a unique pointer over, can we actually get a pointer to it? Okay, and so what you're seeing on the slide, again, 17 lines of code, is some default arguments. You need default arguments for the exam. Some inner classes. Again, you're getting the idea that substitution failure is not an error. Okay, so the reason why you're getting substitution failure is not an error is this version here is attempting to see if we can create a pointer of something. This one here is assuming it's already a pointer. Okay, so there's substitution failure going on there. Okay, but you don't need that for the exam. What you do need for the exam is decal type. What does decal type do? Not necessarily for return type. Figures out the type of something based on an expression at compile time. Decal type figures out the type of something at compile time based on a constant expression at compile time. Okay? So we move on. Inside unique pointer, we have some constructors. We have the unique pointer constructor. Okay? What is this colon MT thing here doing? If we go back up a slide, oh no, I've taken it out of these slides, but okay. We have this thing called _m_t. It's a member field inside the unique pointer class. So what is the constructor with the colon MT doing? Not uniform initialization, no. It's the member initializer list. Okay? So that's the member initializer list. Okay? So that's the default constructor. We come into here. We have here this member function with the standard move sitting there. What does standard move do? What does standard move return? An R-value reference. Why does standard move return an R-value reference? Okay, because you're attempting to move data. Okay. Let's go down here further. Let's actually look at the move constructor for this class. This move constructor for this class, oh no, sorry, I'm looking for a one. The move constructor uses a thing called a standard forward. We looked at standard forward last week in tutorials and also a couple of weeks ago when we were looking at type traits again. What does standard forward do? Preserves reference types. Okay? So standard forward, as long as it's an L value reference, it keeps us at L value reference. If it's an R value reference, it keeps us as an R value reference. Okay? So the standard forward is used in conjunction with standard move to move things around in memory. Okay?
What would happen if you didn't have that there with the standard forward?
We did this in tutorials last week. Go back to last week's tutorial, take out standard forward and see what happens. Okay? If you have a tutorial today, that will be covered off today in tutorials because for Monday shoots are a week behind. Okay? If you don't know, if you have had a shoot this week and you still don't know what standard forward is, go back and look at last week's tutorials. Okay? We have one more example on this. We have this const expression unique pointer taking in a null pointer. Okay, we haven't talked about this null pointer underscore t, but basically it's a null pointer. No except colon colon unique pointer. We have a function, we've got a constructor calling constructor. What's that called? A constructor that on its member initializes list, or where that member initializes list should be, calls another constructor. What's that called? Dedicated constructor, okay? So again, 17 lines of code, just look at constructors. You have, of course, constructors for member initializes list, standard move, standard forward, delegated constructors, move constructors. You should know what all these terms mean. You should know what that code looks like, okay? And you should be able to, again, exam isn't going to have ridiculously complex code like this, okay? There will be some templated code, but I'm not going to have things like static asserts and stuff in there, okay? But you should be able to look at this stuff and basically understand what's going on. Highlight for bits that's going on here and take a look at it. Okay, so again, we have functor, we've got our specialization functor, we have our class, we have our constructors. Let's go take a look at some of our operators. Okay? So we have a destructor. For destructor for unique pointer, okay, uses an auto variable, okay, with a reference to basically get this thing it's referencing, okay? And if the pointer is not equal to a null pointer, then get for deleter, which was the inner class there, and fix it up, okay? So the destructor goes and does some stuff, okay? We also then have operator overloads, okay? So to assign one unique pointer to another unique pointer. Now, the thing about unique pointers is what? What makes unique pointers special compared to shared pointers? They own the object. Well, no, a shared pointer owns an object as well. What is unique, no pun intended, about unique pointers compared to shared pointers? Unique pointers only allow one owner of an object, okay? So when you're doing an assignment, there's a couple of things going on. First of all, you're having to reset or release your ownership over something, okay? It then has to be forwarded, okay? The reason why it has to be forwarded is because what you're owning, you don't actually want to be deleted. You want to pass that ownership on, okay? And so you need to basically forward this object on and then delete yourself. Now, and part of that deleting yourself is you basically want to set yourself to a null pointer, so when delete gets called on you, you don't delete that object, you just passed off that ownership over, okay? The other reason why you need to use standard forward is if you didn't use standard forward, you'd end up calling the copy constructor. Now, I've left it out, but unique pointer does not have a copy constructor. Or it had specialization for the null pointer example, okay? But why doesn't unique pointer have a copy constructor for most types? Should be easy. Because you don't want copies of it, okay? So the standard forward is having to be used to pass the object across. The same applies for assignment in the special case whereabouts something's a null pointer, okay? Also note up here you've got an R value reference, okay? So again, 20 lines of code, and you have destructors, operator overloading, R value references, standard forward, function overloading. Function overloading because you've got two operator equals for two different data types coming in. Okay? Everyone still with me? Yep. Okay, so final slide to do with unique pointer. Okay? Here's some more member functions. We have a function called reset here, which says using standard swap, and then calls swap. But we've also got this member function down here called swap that also says using standard swap. So I've got two things. Again, I've got this function called swap. I've got this using standard swap. What does this using do? What does the using statement do? We had it earlier today. Brings that function into scope. Okay, so there's two different versions of using. There's using namespace standard, which brings everything in the standard namespace into scope. We don't want that. We hate that. We're not going to ever use that. Okay, we use it because it pollutes our namespace. We can just bring a standard, like just a function, into a particular namespace or a particular scoping area. So the using statement between these two braces in this local scope will bring that swap function into that scope at that point. Okay, so we've got this using standard swap. Now, with this using standard swap and this swap function here, what are we trying to achieve on this couple of lines of code? What are we attempting to achieve? So let's look at reset. Okay, reset is in the same scoping area as swap, but reset also says using standard swap. So what happens? Yeah, so it brings the swap into the namespace, okay? But it doesn't hide this one, okay? So it brings the standard swap into the namespace. We have a specialization for unique pointer types here. And so because we bring that using standard swap in there, the next line saying swap, the version that gets called will be dependent on the arguments coming in. Whereabouts, if we just didn't have using standard swap and we called it swap, if this one matches, it would work. If this one didn't match, it would be a compile error. If we just said standard : swap there, then the standard swap would always be called. And so the using standard swap on that line brings the swap function into the same scoping level as this swap function, and then the next line gets called based on whatever the types of these things are. Okay, so using just brings something into scope. And then the rest of it is up to the functions to work out. Okay? So again, on this 13 lines of code, we have member functions, using statements, namespaces, and for STO algorithms. Okay? In the exam, you're not going to see anything you haven't seen in class before. Okay? In the exam, you're not going to see anything you haven't seen in class before. So in the case of STO algorithms, okay, you're probably going to see things like swap or sort or find. Those are the three off the top of my head that we've really looked at. I don't think we've looked at many others. Okay? So what we've done is we've just walked ourselves through the unique pointer code. Okay? So if we go back to here, this, how many lines? This 614 lines of code. Now, I haven't shown you all 614 lines of this code, but you now have the knowledge to be able to read through that 614 lines of code. It might take you some time, but you can work out how this is all working. Okay? So again, I was going to highlight again, each of the things in red down the bottom of these slides are things that you should be revising for the exam. You should, and the things that you should know about them, what they are. You should be able to, in a sentence or two, be able to write down what this thing does. So in our case of talking about the functor, is not just saying a functor is a function object. That tells me nothing. You should be able to say the functor is a class that has the call function overloaded so it can act like a function. That's one mark, and then we can use this with standard sort, for example. Okay? Now, the exam has very little in the way of coding. There is some coding, okay? There is some coding. You will be asked to write maybe a constructor. You might be asked to write a member function. You might be asked to write an operator overload. You might be asked to write a lambda function, okay? So there is some coding, okay? But it will be a couple of lines, maybe 5 lines max, okay? Most of the exam is being able to look at code, be able to read code, and be able to say what the output of the code is, or being able to say what the purpose of the code is. So again, let's just quickly jump across to this week's tutorials that just went up. So last week's, the people with Monday's classes, you haven't done last week's yet. You'll do last week's this week, and the guys on Monday will have a tutorial next Monday. The people on Tuesday and Thursday will have, of course, this week's tutorial. These sort of questions are like for exam type questions, okay? So being able to look at some code here and work out on paper what is the output of this program, okay? And you should be able to read through what that output is, okay? And then for other types of questions are things like, here's some code, so here's 3 lines of code. Explain the differences in the meaning and effect of using the word const here, and here, and here. Okay? So those are the exam-like questions that you'll get. There isn't there isn't a question like code me unique pointer.h. Okay? I'm not going to ask you to code me unique pointer.h. Okay? Any questions at this point? Again, next Monday, there is a lecture next Monday that will go into more details over the exam. We might even do a little bit more revision, okay? But I'll give you hopefully more exam details on Monday. Okay, but this should highlight, if you don't understand what any of these things down the bottom in red are, you should revise them this week, or if you're really stuck, you should send me questions this week because you're probably not the only one who's really stuck. And for next week's lectures, I might attempt to, again, like I did with the type traits earlier today, bring back up those slides and show you things. Okay, so I've got 9 minutes to go. I'm going to talk very quickly about performance and a way in which you could have done assignment 3 to make it work pretty quick. Okay? So I've got a bit of a stupid statement here. Writing code is easy. Writing fast code can be difficult. Okay, so writing code that does stuff, and you probably find this with assignment 4. Writing code is easy. Writing code that's fast can be really difficult. There's a lot to think about. And sometimes there's a trade-off between memory and execution time. Okay? So sometimes you really want to minimize your memory, and that means you might have to do more execution time to, say, look up and find things. Sometimes you want to minimize your execution time, so you end up storing duplicates in memory everywhere. There's a trade-off between memory and execution time. Things to keep in mind. References and pointers can minimize memory copies. Okay? So using references and pointers can minimize memory. However, I just mentioned this to someone during a break. Assignment 4, this isn't strictly true, because assignment 4, you're asked to go and sort some ints, okay? Now, we're running this on a 64-bit machine, okay? But a Linux 64-bit machine. What is the size of an int on a Linux 64-bit machine? Anyone know? It's 32 bits, at least on the school machine. So the size of an int, even though it's not a 64-bit machine, on the school systems, is 32 bits. Okay? What's the size of a pointer on a 64-bit machine? 64 bits. A pointer on a 64-bit machine is bigger than an int on a 32-bit, than on a 64-bit machine. So in assignment 4, if you've got containers of pointers because you think you're being smart, you might not be. Okay? But generally your pointers are much smaller than your objects, okay? Also, things to keep in mind when we're talking about performance. Different containers have different performance for different operations, or even for the same operation. So inserting on a vector and inserting on a map have a different level of complexity, okay? So actually, can someone tell me that? What's the complexity for an insert on a vector? It depends, but what is the standardized insert time for a vector? Yeah. So if you push back on a vector, it's constant time because it goes right to the end, except for if a resizing happens. And if you insert into the middle, okay, it's in because you have to insert that thing, you've got to shuffle everything down. Okay? What's the insertion time for a map? It depends again, yep.
It's find and insert, and it's log in.
Yep.
But if you want to just insert without worrying about creating new element, exist or not, then it's constant.
Yeah, again, for short version, for short version is it depends. Okay? Now, what's the lookup time for an item in a vector? N? What's the lookup time for something in a map? It's log in. So the lookup time for a map is much faster than a vector. Okay? Now, other things to keep in mind when talking about performance. Okay? The optimizer, so when we compile, we put like the dash capital O2 flags on, the optimizer can dramatically improve code performance. Dramatically. My version of assignment 4, the optimizer turned off, takes me about 2 or 3 seconds to run my code. Optimizer turns on, takes me under 1 second. Okay? So the optimizer can really improve your code, but the optimizer is only as smart as I suppose we are. And also we should think about performance and how we can write our own code to go fast, because the faster we write our own code, the faster the optimizer can take it. We shouldn't be relying on the optimizer the entire time. So, I'm really running out of time, but let's talk about designing the graph container. Okay? So let's talk about how we store for node objects. Okay? Questions we might ask, and hopefully you did ask when you're doing assignment 3, is should we create a wrapper class around the node objects? Okay, so should we create, say, a class node that wraps the type in? If we have a wrapper class, which we should do, if we have a wrapper class, should that store objects of type n, or should it have smart pointers around n? A smart pointer is an object itself, okay? So we end up putting more complexity into our code, but we might end up minimizing memory in the long term because we don't end up storing duplicates. What sort of container should we store raw nodes or node wrapper objects in when we're building this? Vectors, maps, etc. Okay? And what are we going to do with the nodes in this container? Are we going to insert? Are we going to delete? Are we going to find? Okay? Because that's going to influence our decision about what we're going to do with the nodes. The same applies for edge objects. Do we need an edge wrapper class? If we have an edge wrapper class, where should it be declared? What's the interaction between the edges and the node classes? Does the graph need direct access to the edges? And then, and I want to poll you guys in a second, should we store a big container of edges in the graph or many small containers in each node wrapper class? So what I mean by that, how many people in their graph, okay, not inside their node, how many people in their graph created a big container, be it a vector or map or whatever, of edges? Okay. How many people created in their graph, say, a collection of nodes, and inside their node, so each node had a small vector or something of the edges that was connected to? Okay? What's the performance difference between those two different designs? Think about this. The number of edges a singular node has, okay, the number of edges a singular node has is going to be much smaller, or at least equal to, if you just have a particular class, but generally much smaller than the number of edges in the entire graph. So if I've got one big container across the entire graph of all edges, that's going to be much bigger than just looking up, finding a singular node, and then finding a sub-container of edges there. Okay? So performance-wise, that second option is a much better design. Okay? And also it's a better overall object-oriented design as well, because it encapsulates the stuff better. Okay, I've got 2 minutes. I'm going to try to go faster. Here is my node class. I've got my graph. It's got an inner class of nodes. It's got a shared pointer over the node data. It's got a list of edges. My list of edges, I do not have an edge class. I just use a thing called a standard pair. Okay? It stores for weight element E, okay, because for E didn't need to be a smart pointer because I've only got one of them for each edge. It has a weak pointer across to the node it's connecting to. The reason why it's got a weak pointer across the node it's connecting to, it means I can delete nodes and don't have to worry about fixing up this list. However, this list is mutable, so when I discover that something is in this list, at that point I can delete. Okay? So my node data is a shared pointer. As for my iterator uses weak pointers over for n objects.